Hello everybody, this is Sareem from Exam Help Web. Today I'm solving Physics May June 2019, Paper 2, Variant 1. Our very first question is define velocity. Our answer is change in displacement by time taken. Part B, the speed v of a sound wave through a gas of pressure P and distance is and density P is given by the equation V is equals to root of Kp by density, where K is a constant that has no units. An experiment is performed to determine the value of K. The data from the experiment are shown in figure 1.1. Part 1, use data from figure 1.1 to calculate K. So now in order to calculate K, we need to arrange our equation. So I'll rearrange my equation and we'll make K the subject of the formula. I'll make K the subject of the formula. So my equation would be K is equals to V square density divided by pressure. After you substitute your values in their respective places, you'll get an answer 1.42. Part 2, use your answer in B, Part 1 and data from figure 1.1 to determine the value of K with its absolute uncertainty to an appropriate number of significant figures. Now over here I should mention the rule, since in the question since in Part 1 we rearranged the formula and made it V square into density divided by pressure. Over here what we actually are doing is we are multiplying or dividing values. So in absolute in uncertainties, whenever we are multiplying values or dividing values, we always take their percentage uncertainties and we add them up to get the total absolute or percentage uncertainty for the answer. So in this question we have already got the answer for our K. Over here how we'll calculate the percentage or absolute uncertainty for our K is we'll add up the uncertainties of V. We'll multiply the percentage uncertainty by 2 for V because we are taking V twice. So this will be 3 into 2 plus the percentage uncertainty of our density, which is 4, plus our percentage uncertainty of the pressure, which is 2. We'll add them up and the total percentage uncertainty for our K will be 12%. Since the question is asking us to get the absolute uncertainty for our answer, we will convert this percentage uncertainty to absolute uncertainty for value K. So we'll divide 12 by 100 and then multiply it with our value K to get the absolute uncertainty for K, and this will be equal to 0.1704. Since the question is asking you to make it to an appropriate number of significance, by this they mean you have to look into the table given above, and when you see here the uncertainties given over here are up to 1 significant figure, and your other numericals over here in the column of values, they are given to you up to 2 significant figures. So now you need to convert this absolute uncertainty to 1 significant figure, so it will be 0.2. This is the absolute uncertainty for our value K, and we'll make our value of K 1.4, which is 2 significant figures. So over here I'll write 1.4 and over here I'll write plus and minus 0.2. Now coming towards question number 2. A block X slides along a horizontal frictionless surface towards the stationary block Y as illustrated in figure 2.1. So there is this box X and there is this box Y. Y is a stationary box, which means it is at rest. It is not moving at the moment. X is moving towards Y with the momentum 0.4 kilogram meters per second. There are no resistive forces acting on block X. This means the surface is a smooth surface. There is no frictional force acting on box X as it moves towards block Y. At time t is equals to 0, block X has momentum 0.40 kilograms meters per second. A short time later, the blocks collide and then they separate. So the graph has been given to you. On the graph, they have given you a graph of the motion of block Y. From the graph you can see that until t is equals to 60 millisecond, block Y is on rest, and then right from here it starts moving with constant change in momentum, and then it stops at t is equals to 100 millisecond, and then it again comes onto rest position. Now moving on to our main question, which is define linear momentum. Part A, define linear momentum. Our linear momentum is mass into velocity. So I'll mention it over here, mass into velocity. B, part 1, use figure 2.2 to determine the time interval over which the blocks are in contact with each other. So earlier in the question they mentioned that block X is moving towards block Y with momentum 0.40 kilograms meters per second, while block Y is on the rest position. And on the graph, when you see block Y is at rest until t is equals to 60 milliseconds. So from this point until this point, they are both connected to each other, they are both in contact with each other. Time interval for their contact is 40 milliseconds, and that's what is given in the graph. You can make it out from the graph very easily. So I'll write over here 40 milliseconds. Now moving on to the next part, which is describe without calculation the magnitude of the acceleration of block Y from time t is equals to 80 milliseconds to t is equals to 100 milliseconds. Now t is equals to 80 and then 100. Okay, so the block Y is gonna move from here until here. Okay, they're asking to without any calculation, you just have to give a statement for it. So I would say that because the momentum is increasing and it is increasing at a constant rate, so I would say that acceleration is constant as well, because change in momentum is also constant over the time period they have given you in the question. So I'd say I'd go with acceleration is also constant within this time interval, within t is equals to 80 milliseconds to t is equals to 100 milliseconds. So I'll write over here acceleration is constant. Okay, second part, time t is equals to 100 milliseconds to 120 milliseconds. From 100 to 120 milliseconds, I see that there's this horizontal line, which means the momentum, there is no change in momentum, means it is at rest position, and when it is at rest position means acceleration is 0. Since there is no change in momentum. Part C, use figure 2.2 to determine the magnitude of the force exerted by block X on block Y. So force is equals to change in momentum divided by time taken. So this is the force block X is gonna exert on block Y, and within that time duration, what is the change in momentum? We'll take that from the graph. The question is asking you to find the magnitude of the force which is exerted by block X on block Y. So change in momentum divided by time taken. So the change in momentum with us is from 0.0 to 0.5, and the time duration for that change in momentum is from t is equals to 60 to t is equals to 100. So the time duration we have over here is 40 milliseconds. Now we must convert milliseconds to second. So as I go down, I'll write that our force is equal to our change momentum was from 0 to 0.5. So 0.5 divided by time taken was 100 milliseconds to 60 milliseconds to 100 milliseconds, and I will also convert this to seconds because that's the SI unit. So 10 to the power minus 3, and my answer would be force is equals to 12.5 newtons. This is done. Now part D. On figure 2.2, sketch the variation of the momentum of block X with time t from t is equals to 0 to t is equals to 160 milliseconds. In the question earlier, they also told you that block X has a momentum of 0.4, means initially when it is moving towards block Y, it is moving with momentum 0.4, and it moves until 60 seconds, because that's when they both get into contact with each other. So until 60 means this line, and then okay, so I'll draw as accurate as I can. I'll draw it here. Okay, so it has to be exactly on 0.4. It will keep on moving with 0.4 momentum. It will keep on moving, and then until t is equals to 60 milliseconds, and that's when they get into contact with each other. Now this will start decreasing, so this will decrease until 100, and this should reach negative 0.1. I'll tell you later why. Okay, it should touch negative 0.1 and then 100 on the x coordinate, and then it will move, and then it will move straight until 160 milliseconds. Now let me describe this motion of block X. In the question, they have already told you that it moves towards block Y with initial momentum is equals to 0.4 kilograms meters per second, and that's what I drew until t is equals to 60, because that's when the both the blocks get into contact with each other. Block X starts with 0.1 less than block Y, so it ends at 0.1 more than block Y did. So that's why when block Y had an end at 0.5 kilograms meters per second, and block X block X started at 0.4, so it will end at negative 0.1. It can't end at 0, because then there will be a change in forces, and then at t is equals to 100 milliseconds I ended the journey, and then it kept from t is equals to 100 onwards. It remains on its rest position. I hope that is clear to you. So moving on to question number 3. The variation with extension x of the force F acting on a spring is shown in figure 3.1. So they have given you a force versus x graph, force versus extension graph. The spring of unstretched length 0.4 meters has one end attached to a fixed point as shown in figure 3.2. Okay, so there's this unstretched length, means the original length of spring, and then there's this stretched one with a weight of 2.5 newtons which is acting down. A block of weight 2.5 newtons is then attached to the spring. The block is then released and begins to move downwards. At one instant, as the block is continuing to move downwards, the spring has a length of 0.72 meters as shown in figure 3.3. Assume that the air resistance and the mass of the spring are both negligible. A. Part 1. For the change in length of the spring from 0.4 meters to 0.72 meters, use figure 3.1 to show that the increase in elastic potential energy of the spring is 0.64 joules. So the formula for elastic potential energy is half into force into extension. If you do not have force, you can take it as half into spring constant into extension square into our force was 2.5. Multiply that to your extension, which is 0.72 minus 0.4 closed. Our answer would be 0.64, and that's what they asked you to prove. Moving on to the next part, calculate the decrease in gravitational potential energy of the block of weight 2.5 newtons. The formula for GPE is m into g into h. this has already been given to us, that is 2.5, and then height difference is 0.72 minus 0.4, and then our answer would be equals to 0.8 joules. So moving on to part B, use the information in A part 1 and your answer in A part 2 to determine for the instant when the length of the spring is 0.72 the kinetic energy of the block when it was an original length of the spring. And okay, so initially when it was at height 0.4, when there was no block loaded onto the spring, at that height the spring possessed only GPE, gravitational potential energy, at height 0.4 meters, which gets converted to electrical potential energy and some other energy when this spring stretches. So initially it was just gravitational potential energy, so I'll write that. When it got stretched, this energy converted into electrical potential energy and then kinetic energy. Gravitational potential energy we already got from our first part, and then elastic potential energy was also given in the second part. So our kinetic energy is equal to 0.16 joules. Now in this question, in this part they're asking you to find the speed of the block. Now that you have your kinetic energy, and the formula is kinetic energy is equals to half into m into v to the power 2. You already have got your kinetic energy, which is 0.16 is equal to half m. You can calculate with the help of the formula force divided by acceleration, which will give you 2.5 divided by 9.81, and then you'll multiply it with your v square. Hence your speed will be equal to 1.12. A spherical oil drop has a radius of 1.2 into 10 to the power minus 6 meters. The density of the oil is 940 kilograms meter per cube. Show that the mass of the oil drop is 6.8 into 10 to the power minus 15 kg. Okay, so we have mass, we have density. So we can write the formula, which is with us density is equals to mass divided by volume. Now since we don't have the volume, but we can calculate it with the help of the radius given, and they have also stated that the oil drop is in the shape of sphere. So the volume for sphere is sphere volume is equal to 4 by 3 into pi into r, which is radius to the power cube. So the volume would be equal to 7.24 into 10 to the power minus 18 meter cubes. Now that you have the volume, you can use the formula mass. You can use the formula density into volume to get the mass, and your mass will be equal to 6.8 into 10 to the power minus 15 kilograms. Part 2. The oil drop is charged. Explain why it is impossible for the magnitude of the charge to be 8 into 10 to the power minus 20 coulombs. One electron or a charge can only be of 1.6 into 10 to the power minus 19 coulombs. A charge or one oil drop can only be of 1.6 into 10 to the power of minus 19 coulombs. It cannot exceed that, or it cannot be any less than this. Okay, part B. The charged oil drop in part A is in a vacuum between two horizontal metal plates as illustrated in figure 4.1. Okay, you see this charged oil drop in between these two charged plates. This is a positive charged plate and this is a negative charged plate. This is negative because this is earthen, and this is being given positive, so this becomes positive plate and then this becomes negative plate. Distance between these two plates is 8 millimeters. The plates are separated by a distance of 8 millimeters. The electric field between the plates is uniform and has a field strength of 2.1 into 10 to the power of 5 volts per meter. The oil drop moves vertically downwards with a constant speed. Part 1, calculate the potential difference between the plates. Now that we have been given electric field strength and we have the distance between the plates, we can use the formula electric field strength is equals to voltage divided by distance between the charged plates, and then we can rearrange this and get the value for voltage, which is equal to 1.7 into 10 to the power 3 volt. Now I'll proceed to part 2, explain how the motion of the oil drop shows that it is in equilibrium. Now this statement is very useful to us. Over here they describe that the oil drop moves vertically downwards with a constant speed. Whenever they say constant speed, something moves with a constant speed or remains at rest whenever there is no resultant force acting on it. So over here it is mentioned that it is moving at constant speed, so this proves that it is in equilibrium. There is no resultant force acting on it. So I'll write that over here. Since it is mentioned that it is moving at constant speed means no resultant force is acting on the oil drop, or no acceleration, hence it is in equilibrium. Now moving on to part 3, determine the charge on the oil drop, and this is of how much marks? 3, and they're also asking you to find the sign of the charge. So for first, finding the charge of the oil drop. Okay, so first of all we need to look at the things which have been given to us. We have been given the distance between the plates, we have been given the mass of the oil drop, we have been given the electric field strength. Okay, so we'll make use of these values probably because we don't have any other way to find out the charge. What could be there? What formula could I be using over here? Okay, so this is the charge and mass is also there, means some weight of it is acting downwards. And okay, so there is this electric field strength, this is negative and this is positive, so the electric field direction would be downwards too. Okay, so this means some electric force would also be acting on this charge, whether negative or positive. Some electric force will definitely act on it, and weight is also acting on it. Since this is an equilibrium, means they both will be opposite in direction. When weight is moving downwards, electrical force would be acting upwards. So what I can do is, it's in equilibrium, so I'll write over here, since it is in equilibrium, I'll write electric force acting on the oil drop is equal to its weight, only when it is in equilibrium. That is mentioned in the question. Electric force is equal to electric field strength into its charge, which is equal to mg. Electric field strength into charge, electric field strength is also given to us 2.1 into 10 to the power 5, and charge is still unknown to us, so I'll write that exactly here. And then is equals to its mass is being given to us. We'll multiply that with 9.81, which is the fixed value for g. So this is 6.8 into 10 to the power minus 15. We'll multiply this with 9.81, and our answer for charge will be equal to 3.18 into 10 to the power minus 19 coulombs. Don't forget mentioning the unit, because this will lead you to losing some or maybe whole of the mark. Now they are also asking you to find the sign of the charge. As I mentioned earlier, that the question says it's moving with constant speed, means it is in equilibrium. I would say this is a negatively charged oil drop, because that's when it would be acted upon by a force which will act upward towards positive plate, and due to its weight it always tends to make things move down. So some force will definitely act upwards. If both the electric force and weight were acting down, then there will be no force to balance the oil drop. Consequently, it won't be in equilibrium then. Since it is mentioned in the question that it is in equilibrium, one force has to act down and the other one has to act upwards, and we all know that weight always acts downwards, so electric force would definitely point upwards, and this will be then a negatively charged, so that it gets attracted towards the positively charged plate and then it tries moving up. So I'll write that over here. It's a negatively charged particle. Okay, moving on to part C. The magnitude of the potential difference between the plates in part B is decreased. Explain why the oil drop accelerates downwards. Okay, so the relationship between electric field strength and potential difference is they are directly proportional to each other. When voltage decreases, definitely electric field strength would decrease too. When electric field strength decreases, the intensity of the electric force on the oil drop to make it move upwards would also decrease. As a result, forces will get imbalanced, and then the downward force, or weight you could say, will overtake the upward force. Hence, oil drop will accelerate downward. So I'll write that over here. Electric force acting on the oil drop will decrease. Forces get imbalanced. Weight is now greater than the electric force, and hence the oil drop moves downwards. Okay. Part 2. Describe the change to the pattern of the field lines representing the uniform electric field as the potential difference decreases. As the potential difference decreases, electric field strength also decreases. Hence, the separation between the field lines will increase now. Part D. Two types of force, X and Y, can act on an oil drop when it is in air, but cannot act on an oil drop when it's in vacuum. Force X can act on an oil drop when it is stationary or when it is moving. Force Y can only act on an oil drop when it is moving. State the name of the force X, force Y. The very first force which comes into my mind when something is moving in air is resistive force, or air resistance, or whatever you want to say, that frictional force. So, and that is one force which acts only when an object is moving, but not when it's on rest. So I'll say that force Y is air resistance. And there is this one more force which could act on an oil drop, and it will act on an on the oil drop whether it's in its stationary position or it's moving, and that force is none other than the upthrust. That's one force which will act on an object whether that object is moving or at rest position, but air resistance will only act on that object when that object starts moving. Now if you want to watch rest of the video, you can visit our channel Exam Help Web.